got some of the tape. Hold on. Gosh, trying to wonder if maybe the skeeters are working. Okay, how about this guy? Do we want to look at this? Match the graph of the function on the right with the graph of its derivative. What's that derivative going to look like? Those of you who are good. It's going to be a straight line. It's going to be, and this one, we could even do this one numerically. What is the slope of that line? 1. So where should the derivative be? At 1. Good. Okay, so it should be that guy right there. Okay. Right. Okay, how about something like that? Same kind of deal. This one you can't do numerically, but what should that look like? Assuming that's a uniform change, what's the derivative going to do? Starts off as what? Describe the derivative right there.
It's going to start as low, no matter how you negative number.
Low, okay, so it's going to be a large negative,
And it's going to go to a
small negative, what is it there?
0.
Small positive, bigger positive, bigger positive, bigger positive. So which one matches that?
A.
A would, right? Everybody see that? Okay, because it starts, remember the value of the derivative is equal to the slope of the function. So this matches it. Large negative, lesser negative, 0, greater positive, greater positive, greater positive values, right? Questions on that? Okay. Something like this. How would you go about doing this one? What would you probably do here? What would be some key points you could use?
Where it crosses the x-axis.
I-
The highs and the lows.
Yeah, I'd say, I wouldn't say where it crosses the x-axis. Other ideas. Quincy, you have an idea? No. What are some key points that we could?
It's highest and lowest.
Okay, yeah, the places where it has horizontal tangents. So does that make sense? So right there, the slope is 0, right there it's 0, and right there it's 0. So what should the derivative function be doing at those places? Good, crossing the x-axis, yeah, right. It should have 0 values. Because the slope of the function is the value of the derivative. And then otherwise, I mean, the derivative is going to have kind of the same look, isn't it? It's just going to go from 0, it's going to get more negative, more and more negative. There's its biggest negative value, and it gradually gets less negative and goes down to 0, right? Gets more and more positive, goes back to 0. So it really matches this guy, doesn't it? Right there, we should have a 0, a little bit for a small negative number, and we do, right? Should have a 0 a little bit to the right of the origin, and we do, right? Does that make sense? Okay. Okay, how about something like that? At what points, we're trying to figure out at what points, can I make this thing? Yeah, there we go. At what points does the function appear to be differentiable? Okay. So every place except, where is it not differentiable? At 1, at 3, and at 5. Agreed? Okay, so then how would we say that? Okay, so how am I going to... So does this, it's going to be quicker here. Does this... Oh, made a new one. How's this? How do I get this thing to just... Oh, there we go. Show this. Oh, except. Right, so it wants the values except. Okay, so So I see what the, right. You guys saw that, I didn't. So let's do this one. Where's this one gonna be? 2, 4, and 6. Okay, why at 2, real quick? Okay, sharp corner or cusp, either or, right? Why not here? Okay, there's a discontinuity, right? Any place there's a discontinuity, it can't have a derivative, right? Differentiability implies continuity, okay? But here's an example of where it's continuous but not differentiable. What about at 6? Jump, good, discontinuity, right? A jump discontinuity. So once again, those won't work. Okay, how about where does the function appear to be continuous but not differentiable? 2, okay? And finally, neither continuous nor differentiable at the other 2, right? 4 and 6, okay? Yeah, I like it. I like it better like this. Yeah, okay. Next. How about this guy? Find all values of x for which the function is differentiable. So we want to find all of them except the places where it's not. How would we go about doing this problem? Okay, we're going to factor the bottom, and then we want to know if tell me the places where it's not going to be differentiable. What's going to, okay, where the bottom's 0, right? Does that make sense? Where the bottom's 0, the function can't be defined, right? Does that make sense? Okay, so then our answer, if we factor the bottom, what are we going to get? 8 and -5, yeah, so B, all real numbers except 8 and -5. Does that make sense? Okay. All right. How about this guy? If we're going to differentiate, okay, let's talk about this one. So here's a problem where we're trying to find the derivative. Now, there's a lot of ways to do this one, but we want to, most of calculus is not about doing the calculus, it's about doing it easily. So what's going to be the best way to do this one? For sure. Good, we'll expand the top out, and then what? Good. Separate the fractions, and in each fraction, each term is going to have an x cubed on the denominator. So we'll just simplify each term by using the property of exponents, right, and subtracting 3 from the power of x on the top. Okay, if there's any of these we want to do, tell me, and we can go through any of these we want to. Well, like for example, what if we had the function? What if we had one of the terms was 4x over x cubed? What would that simplify to? Yeah, if I had 4, say it again. 4x to the -2, yeah. Does that make sense? And so the goal is then, on something like this, I mean, this looks like it's trying to coax you into doing maybe the quotient rule, and maybe even the quotient rule where the derivative at the top involves a product. But those rules are complicated, right? We would rather take the time to expand this out and write it as a string of terms that use the power rule. And I think you've seen this, as you've gone through and done this stuff. If we were to just brute force this thing with the quotient rule and the product rule, we're going to get a whole bunch of terms in our answer that are very complicated to put together. It makes a lot of work, a lot of post work instead of a little bit of pre-work, right? Does that make sense? Okay, so that's the moral of that story right there is don't just jump in and do quotient rule there. Okay, so what about this? Find an equation for the line tangent to the curve at the given point. So this is just a sneaky way of having you differentiate, right? And then do something with the derivative. But something you do with the derivative isn't that big a deal. Once again, how are we going to do this derivative most easily? Yeah, we're going to split it up, aren't we? So this one's going to look like, if we start with y equals x cubed plus 1 over 8x. Yeah, we'll just split this up. Right, so we'll write this as x cubed over 8x plus 1 over 8x. So what's that term going to become?
Squared 8x.
But what about the 8 on the bottom? What do I do with the 8 on the bottom?
1/8.
1/8, yeah. Just pull that stuff out front. And then I've got an x squared, right? Good. Plus 1/8 to the -1. Good. So then y prime equals, what am I going to get here?
1/4 x.
Yeah, 1/4 x. Good. Everybody see that? Okay. And then here I get minus 1/8 x to the -2nd, which means we could just put that x squared on the bottom if we wanted, right? So what's that do then if we're evaluating this when x equals 1? What's this? So what's this going to equal when x equals 1? What, 1/4 minus 1/8? So 1/8. Right? So there's our slope of our tangent line. How would we get the point of tangency?
Plug in 1 to the original.
Yeah, plug in 1 to our original function, right? That's going to give us 2 over 8, so 1/4. Do that right? Yeah. So we get the point 1/4. The slope of the tangent line is 1/8. So, and what would we do there then? Get the equation of the tangent.
Slope y equals m.
Yeah, y equals mx plus b, right? So 1/8 x plus b. We could plug in 1 and 1/4 for y and x respectively and find b, right? You good with that? Okay. All right. Parse again. Horizontal tangents, what's that going to involve? What's unique about a horizontal tangent? Slope is 0. Okay, right. So then remember that that's what a derivative function does, right? The derivative, the value of the derivative equals the slope of the function. So we could find those how then? Yeah, good. Find the derivative and set it equal to 0. And would everybody agree that's just going to give us a quadratic equation, right? If I differentiate a cubic, right, that's going to drop down the leading term is now going to be an x squared term instead of an x cubed term, right? So we're going to get a polynomial, but it's going to be a second degree polynomial. So we'll end up with a quadratic equation, and when we set that, or a quadratic function, when we set that equal to 0, we just got a quadratic equation in standard form, right? And you can solve that any number of ways. I think these turn out to be, factorable ones, right? Worst case scenario, though, you could just, you could use a quadratic formula or something and throw them into a scientific calculator. But I think, yeah, it wants an integer or a fraction. So these are going to work out. They're going to work out nicely. Okay. Question on that? Okay, you good with that? All right. Derivatives of all orders, what are they getting at here?
Keep going until.
Yeah, just keep going. And these are, do you see that this is, I mean, are you getting to the point where you could look at this now and say, oh, that's easy, right? Because you can differentiate term by term there, right? And so you're just using the power rule, right? So you recognize that that's not going to be hard. Eventually, you're going to get down to where the higher derivatives are just going to be zeros, yeah, right? Okay, let's see. All right. Yeah, that's good. So then, this is really no big deal. It's just an application of our derivative rules. Should we go through one of these? So then, what are we going to have when I differentiate this? I'm just going to differentiate term by term. What's the first term going to give me? 20. And then the second term just uses one of our other rules. Yeah, what's the derivative of cosine?
Negative sign.
Negative sine, so I would just get minus 9 sine x. Okay, that's it. Should we, you tell me, okay, there's an option to look at. So there's an option to look at, and let's go back. So between those two, do you want to go through either of those two?
If you're factoring on the test and it doesn't come out evenly to nice numbers, can you graph it?
This is a non-graphing test, but like, should we go back to that one? To, whoops, to,
I'm just wondering.
so these, yeah, I know that these will come out because it says your answers are going to be integers or fractions. So it's guaranteed to either factor. Should we just go through one?
Oh,
So
I'm
we can,
just doing like my practice test and it doesn't come out.
well, okay, it's going to factor, but it's not going to be an easy one to factor. So let's look at this real quick. So if I were to differentiate this, you guys tell me real quick, what's the derivative going to be?
3x squared
3x squared.
minus 10x plus 8.
Okay, so that one doesn't look very good, does it? I mean, it's going to factor, but a is not equal to, we can't factor out a GCF. A is not equal to 1. So when we set that equal to 0, that's not super easy to factor. So real quick, what are our options on charging through a quadratic equation like that? So we could use the quadratic formula. We very easily could. And if we do, it's going to work out. Let's just do that once. You can. So let's look at this two ways. Let's look at it first. Let's go through this because we haven't done this year yet. Let's just review how do we deal with solving a quadratic equation in standard form if we're not able to graph it. So one thing we could do is we could just use the quadratic formula. So we'd get to find the solutions, x equals what in this case? 10, so negative b plus or minus square root of b squared, so what's that? 100, everybody see that? Minus 4 times 3 times 7. So let's make that 4 times 3 is 12, times 7 is 84. All over 2 times 3, so over 6. So that's going to give us 10 plus or minus square root of 16, which is 4. And so then all you have to do here is we're just going to split this into the plus. And so we're going to get, what, 14 over 6 is 7/3. If I subtract, I just get 6 over 6. So if I take the minus, I get x equals 1. Okay, so we can do it that way. But what about using bottoms up too? That's the one I wouldn't mind just reviewing that with you real quick. Bottoms up. Do you remember bottoms up? Oh, bottoms up is huge. Bottoms up is really good. So bottoms up, when we have a quadratic equation in standard form where a is not equal to 1, you can see right away if it's going to factor. I mean, if it may not factor, like if we had had a discriminant here that wasn't a perfect square, we would have had to leave this in terms of square roots, right? Which is fine. I mean, those are exact answers, and that's okay too. But this one's going to work out. So for bottoms up, we do a times c. 3 times 7 is 21, and so we're just looking for magic numbers, like we always would, that multiply to AC and add to B. So B is negative 10. What are the numbers that multiply to positive 21 and add to negative 10? Negative 3, negative 7. Okay, so then what that tells us is, bottoms up, that tells us that we're going to start off with the magic numbers inside this factoring template. So minus 7 and minus 3. And then what's the next step in bottoms up? Okay, good. So whatever A is, you're going to divide each of those numbers by 3. Now you're going to reduce fractions and, if necessary, go bottoms up. So when I reduce these, negative 3 over 3 just is negative 1, right? So this guy just becomes x minus 1, done. But this one won't reduce. And so if it doesn't reduce, we just go bottoms up. We're going to take the denominator and make that the coefficient of x, right? So this one becomes 3x minus 7. And so our solutions then, by applying the zero product property, would just be 7/3, right? Or 1. Okay. Do you see a shortcut in bottoms up if you're not trying to factor but just get solutions? We could just, without going bottoms up, we could just set these equal to 0 and solve, couldn't we? Right? And just get 7/3 and 1. Okay? Does that make sense?
Yeah.
Page that help?
Yeah.
Okay.
I just wanted to know if I could craft it or not.
Oh, I got you. Okay, so that was way overkill. All right. How about then, did that. What's this going to be? When I differentiate this, what's going on here that's slightly different?
The x squared.
Yeah, this is just product related, right? Because I've got an x squared times the sine x. So if we calculate y prime, derivative of 24,
Is 1.
0, that goes away, right? But what about this? A couple things we can do with that. Minus 6 times x squared times sine x.
It would be 6x plus
Oh, do you have to do the
Yeah, what do we do for that? Product rule. Okay, what about the negative 6? We could group it with the x if we want to, but we also could always do what with a constant?
Just take it in.
Take it in front. Right, so we could write this then as y prime equals negative 6 times whatever we're going to get from the derivative of that product, right? So what's the product give us?
2
Okay, so we're going to take the derivative of,
x squared and sine.
okay, yeah, in any order you want to, because it's plus. I usually say the first times the derivative of the second. So x squared times, what's the derivative of sine x? Good. And then plus the second times the derivative of the first. What's the derivative of x squared? Okay, and so then when we recombine all this stuff, what do we get? Well, negative 6 times, we could redistribute the negative 6 too then at that point if we want to. So negative 6 x squared cosine x minus 12x sine x. Okay. Does that make sense?
And that's the answer.
Yeah, that's the answer. That's all they're looking for. They just want us to differentiate. Same thing here. They just want us to differentiate. Oops. What about this one? What do we do here?
Change it back to
Yeah, I mean, you could. That's an option. You could change the cosecants to sines. We don't really have to anymore, though, do we? Because we know the derivatives of the other 4 trig functions, right? So what form is this in, though? If I'm going to differentiate this, if I have y equals cosecant divided by 1 plus cosecant, well, what's the pattern I have to follow there?
quotient.
That's quotient, isn't it? Right? I have to follow the quotient rule. So then y prime is going to equal bottom, right? Times derivative of the top. What's the derivative of cosecant? Cosecant, cotangent, but when we take derivatives of co-functions, we always get negative. Good, those are the negative ones. So negative cosecant x, cotangent x. Okay, keep going. So bottom times derivative of the top. Low D high minus, good, high D low. Derivative of the bottom is same thing, isn't it? Yeah, because the derivative of 1 is 0. Okay, and then what's the other part of the quotient rule? Can't forget? Okay, good. Low squared, so quantity 1 plus cosecant x squared. So if we go ahead and distribute,
Wait, don't we not? We don't with, we don't distribute.
on the bottom, the squared,
Just leave it there because we can't talk.
leave it. Yeah, just leave it, right. That bottom, that's going to be a mess to expand out. And remember, when we're taking derivatives, and you guys haven't seen this a ton yet because we haven't really applied these derivatives, but we would prefer to leave them in factored form, right? We really don't want to unfactor them. We don't want to expand them because then that's undoing what we're going to need them to be later anyway, right? So on the top, let's see if we can kind of muscle through this. If I distribute this negative cosecant cotangent over here, would you agree that when I multiply by cosecant, I'm going to get a negative cosecant squared cotangent? What about here when I multiply through? Don't I get a positive cosecant squared cotangent? Right? So there's going to be a lot of cancellation. So really all I'm going to get on the top then is just that part, right? Right? I'm just going to get a negative cosecant x cotangent x. And the other stuff cancels over 1 plus cotangent, cosecant, sorry. So that's my answer.
Wait, why don't we like separate the bottom into two of them?
What's the advantage of that?
Cancel the one on the top.
I can't. I can't do that because that would be like saying, okay, here's the suggestion. Tell me if I'm wrong. The suggestion is cancel one of those with one of those. Okay. I can't do that though because they're not like factors. That would be like saying this. If I have 3 plus 4 over 3 times 3, it'd be like doing that. See what I'm saying? We can only cancel like factors, and that's a term on the top. Now, if I were able to factor out a 1 plus cosecant from both terms, then I could cancel it, okay? All right. Let's go through and see, how far are we through this here? Pretty far. We don't have much left. So, finding the second, on this one, they're giving you y. What's probably tricky about this one? Yeah, read it carefully. They want you to find y double prime. So you're going to have to differentiate and then differentiate again, right? So your first derivative is just going to be 9 secant x tangent x, right? Second derivative is going to mean you're going to have to do a product rule from that. Well, should we do this one real quick? I don't know, hopefully we'll have time, but we'll see. Should we do this one? Okay. So y prime equals 9 secant x tangent x, right? So now y double prime, let's leave the 9 out front, and we're just going to do product rule. So we're going to do first times derivative of the second, well that's just going to be secant squared, right, plus tangent x times derivative of the first, which is secant x tangent x, right? So what do we end up getting then? 9 times secant cubed x plus secant x tangent squared x. Now, have you guys, did they take that or did they want you to go further with that?
They want to distribute it.
Okay,
Yeah.
they want you to distribute the 9, but then leaving it like that was okay?
Yes. Yeah.
Okay, all right. And then last one possible, oh, that's no big deal. It's just quotient rule, right? Okay? So that's it. That's the test. No sweat, you can do that.
Spend all of your night doing
Hey, I gotta work tomorrow.
All right, so we'll take a run at this tomorrow then, right?
So I don't think.
All right.
I don't know if it'll be a run, it might be a jog.
Oh, okay. Man, it is cold in here.
It's really cold in here.
And it's not getting any better.
The one good thing about this day is it goes like with best thing out of the day.
Right when you start freaking out about all the stuff you're doing, classes and classes over.
So actual
One of them was at 36.
12, 3,
9-4.
9, 4, 6, 6, or the 6 1.